So this video is going to talk a little bit about some interesting properties of conductors you can figure out with Gauss's law, and we're also going to define capacitors. And this is all in chapter 25-4 of the textbook. Okay, so first off on conductors. So an interesting thing about conductors is that any excess charge must be on the surface of a conductor. And there's a pretty good reason for this. So if you imagine you've got a big, let's say, circular hunk of metal, and it has some excess charge. Well, if they're all excess negative charges, say, well, the negative charges all want to repel each other. So there's going to be a repulsive force. So, and since it's a conductor, charge is free to move around. So the charge has to spread out so it gets as far apart from the other charges as possible. So that means that by definition then, so it has to end up on the surface of your conductor. So if your surface is uniform, say like a nice sphere or something, then the charge is going to be spread out evenly. So if not, actually the charge density will tend to build up and it'll actually be larger at sharp points and edges. So imagine like this is part of how a lightning rod works, right? So if you have a sharp point, the charge distribution is actually, the charge density is larger there. So another thing that has to be true is that in electrostatics, at least, the electric field must be perpendicular to the surface of the conductor. So we know if you have excess charge, it has to be on the surface. So let's say we've got a surface, so imagine this pad of paper is a conductor. So the electric field, well, if we've got some electric field, if it wasn't perpendicular, there's going to be some component along the surface, which means if there's some component along the surface and it's a conductor, charges can move. But we already said we're looking at electrostatics. So if you're in equilibrium, so if you've got a static charge distribution, they can't be moving around, so the field has to be perpendicular. So, and what this all boils down to mean is that if your electric field inside a charged conductor has to be zero. So imagine again, you've got some, say, spherical shell that's a conductor made out of some sort of a metal. So if you've got some excess charge, we know the charge has to go out to the surface. So then you can use Gauss's law. You can imagine drawing your Gaussian surface then inside the conductor. So just inside, so now, well, you're inside the surface, so now there's no charge inside. And if there's no charge inside, then the electric flux inside has to be zero. And again, if it's spherical, so the symmetry says that the field then has to be zero. And this is the basis of something called a Faraday cage, which is actually a way you can shield out electric fields. Okay, so the other thing, and we're going to define a capacitor. So, and we'll talk quite a lot about capacitors this semester, especially when we get to circuits. But the simplest case, the capacitor is just two oppositely charged plates. So imagine you have two plates and you have some excess charge on them. And by the way you usually set up a capacitor is that you have positive charge on one plate, negative charge on the other plate, but the magnitude of the charge is the same. So far away from the edges, so let's say you're sort of in the middle of the plates and you're far away from the edges of the plates, the interesting thing about a conductor is that the field between the plates is constant. And outside the plates is actually the field is close to zero, which is kind of handy if you want to build up a nice uniform electric field. And these are actually, capacitors are useful devices for storing electric charge. And again, we're going to talk a lot more about capacitors once we get to electric circuits.